Now let's take a look at aromaticity. Aromaticity is the very special stability that aromatic compounds have, such as benzene. It has the extra stability that it will not react with most of the compounds under the regular condition. So we have the Hooker's rule that tells you what compound can be aromatic. There are 4 requirements here. The compound must be planar, it must be monocyclic, must be fully conjugated, and with 4n plus 2 pi electrons. The first 3 are easy to understand. Okay, we must have fully conjugated system with pi bonds, but the number of pi electrons is also a requirement. The n here could be any integer. So the number can start from 2, 6, 10, 14, etc. when n equals to 0, 1, 2, 3, 4, etc. So we will see some examples. First, when n is 1, 4n plus 2, that's 6. 6 pi electrons. That's benzene, right? Benzene ring has 6 pi electrons. So benzene ring is flat. It's monocyclic, fully conjugated with 4n plus 2 pi electrons. It is aromatic. It has the extra stability. How about this next ion? 5-membered ring with 2 double bonds and a negative charge. This ion is called cyclopentadienide ion. The anion, the negative charge in the ring, is conjugated with the 2 double bonds, right? So it satisfies all the requirements. It's planar, monocyclic, and it's fully conjugated. And how many pi electrons do we have? 6. We have 2 double bonds, that's 4 electrons. And we also have the negative charge, that's 1 lone pair on the 5th carbon. So we have a total of 6 pi electrons. And the cyclopentadienide is aromatic. Next example, here we have a 7-membered ring with 3 pi bonds and a positive charge on the 7th carbon. This is the cycloheptadienyl-cation. Again, this ion is cyclic, it's planar, it's fully conjugated, right? The positive charge is like an allylic cation, so you can draw several resonance structures of it. It's fully conjugated. And how many electrons do we have? 6 from 3 pi bonds, right? So all these 3 are the examples of aromatic compounds with 6 pi electrons. I just want to give you one example of 2 pi electron aromatic compound when n is 0. Here we have cyclopropynyl cation, 3-membered ring with a double bond and a positive charge. Cyclic, fully conjugated. And we have 2 electrons. It satisfies all the rules for aromaticity, and it is an aromatic ion. All right. Lastly, we want to take a look at a few heterocyclic aromatic compounds. Heterocyclic means we have cyclic compounds that contain at least one atom other than carbon within their ring. And these atoms could be nitrogen, oxygen, or sulfur. So here are a few examples of the heterocyclic compounds. Okay, 6-membered ring with a nitrogen, that's pyridine. 5-membered ring with a nitrogen, that's pyrrole. 5-membered ring with oxygen is called furan. All 3 examples shown here are aromatic. We know they are monocyclic. We know they are flat, and they may be fully conjugated. We will see. And do we have 6 pi electrons? Let's take a look. For pyridine, we do have 6 pi electrons available from 3 pi bonds, right? So there's no problem. And I do want to mention one thing here. The lone pair of electrons on the nitrogen will not be part of the aromaticity. Okay? For pyrrole, we only have 2 pi bonds. That's 4 electrons. So pyrrole will need 2 more electrons in order to be aromatic. Where are those 2 electrons? From the nitrogen. Okay, so when these electrons on the nitrogens are needed for aromaticity, they will be part of it. Okay, so here is the difference between pyridine and pyrrole. For pyridine, the lone pair of electrons is not part of the aromaticity. So it's readily available to be donated to, for example, a proton or to something that's electrified. But in pyrrole, these lone pairs of electrons will be part of the aromaticity. They are not readily available to participate in any reaction. As a result, pyridine will be more basic than pyrrole due to the availability of the lone pair of electrons on the nitrogen. Okay? Now for furan, we have 2 pi bonds, 4 electrons, and we need 2 more to be aromatic. So 1 lone pair on the oxygen will participate in the aromaticity. The other pair will be left out. Okay? And furan will be aromatic. So basically for heterocyclic aromatic compounds, when we need the lone pair to be aromatic, the lone pair will be part of it. When we don't need it, then they won't take part in it. Okay, so I hope from these examples you got some basic understanding on what aromatic compounds are. So can you determine whether or not these molecules or ions are aromatic or not based on the rules that we just talked about for aromaticity, the Hooker's rule? Please note that All of them are monocyclic, conjugated, and planar. What you need to do is to determine how many pi electrons are there in these molecules or ions.